Li from National University of Singapore. I'm very delighted here to share our recent work on generative deep learning-enabled multi-objective synthesis of dual-polarized wide-angle loop family frequency-selective services. The motivation of this work is from multifunctional Markov base stations. The FSS serve for these base stations should be multi-objective. And here's an example. The target includes low insertion loss passband, broad lower stopband, and also need to realize a high error rate between them. And all the specifications should be maintained under dual-polarized wide-angle incidence. Multi-objective design requirements. We propose a generative deep learning-enabled method. We first extract the initial topology and also the rules of symbol generation, and use this to point into the dataset level and also into the deep learning level, and finally we reuse it into the trained generators. The first part of the method is initial topology. We propose a 5-layer loop family element here. To give a third-order passband, we introduce 3 layers of resonance slots, and to enhance the roll rate, we introduce an inter-element slot. And for the further lower band rejection, we introduce other 2 layers of non-resonance slots. And all of this is to give a target-oriented structural pairs into random pixelated symbols. Then we propose our symbol generation rules by 4 steps to give a diverse but physically constant training set. First, we require it to be symmetrical and use the strip atoms. And we force the third layers to be locally different from the first and the fifth layers. And all 3 different patterns should have the Euler number greater than 0. And then we also require the lower bound or the upper bound for the virtual current path. For the training, we propose a multi-channel conditional generative adversarial network, and this model has 2 branches in different dimensions for different layers. And for each channel, we also use the generation rules to weight the updating gradient, and it finally contributes to the weighted generator loss. After training, we post target vectors for final synthesis and input them into trained generators. And we have diverse structural solutions. It means we have different structures, but they all reach the multi-design objectives. And finally, we fabricate the first one for the experimental verification. And all the deep learning-enabled designs has a good performance in their passband and also stopband, and also a high roll rate. And all the results can be maintained under dual-polarized and wide-angle incidence. That's all. Thank you.